Cauchy Euler equation. What is this about? Cauchy Euler equation, it takes the form an(xn), the nth derivative with respect to x, plus an minus 1, xn minus 1, d to the n minus 1 y, dxn minus 1, plus, this goes forever, a1x dy dx plus a0y equals g of x. Now, there's several things to talk about here. The first one is these n and n, they must match. They always must match in this case. There's a 1, 1. There's nothing 0, 0. That's one thing. The other thing is what we have been doing so far, that all these coefficients, like this one, all these coefficients were constant. Not anymore here. No more constant coefficients. That's the difference between this one and the previous stuff we did. And the question is how to solve such equations. For simplicity, I'm going to look at the homogeneous and non-homogeneous second degree. So ax squared, d squared y dx squared. And then I'll show you example at the end of today's lesson if it's third degree or higher. So that's the homogeneous one. The non-homo, it would be the same thing, bx dy dx plus cy equals some function nx, non-homo. So the question is how to solve such equations. Okay, what's the trick to solve them? Well, we start with this. We try a solution in the form y equals x to the m. We need y prime, mx m minus 1. And then we find y double prime, m times m minus 1 x to the m minus 2. Why did I find them? So this is the trick to solve them. So I found them, and because I want to substitute them back into that homogeneous equation, so we have ax squared, instead of d squared y dx squared, which is the second derivative, I found m times m minus 1 x to the m minus 2, plus bx mx to the m minus 1 plus cx to the m. What can we do here? You can multiply the x's, they have the same base, so m minus 1 stays the same, so you get x to the m. Multiply these together, x to the m. We may factor out x to the m. That'll leave am times m minus 1 plus bm plus c. Okay, so up to this point is good. So we say for up to this, y equals x to the m is a solution to the given differential equation whenever m is a solution of this auxiliary equation or characteristic equation. Let me write it again. am times m minus 1 plus bm plus c equals to 0. And if you multiply this out, let's see what we get. am squared minus am plus bm plus c equals 0. We can rearrange this such as b minus am plus c equals 0. So watch how I'm going to do this. I'm not going to memorize this one. We're not going to memorize these. It's just a procedure how to solve this stuff. I'm going to look at the first case where m1 and m2 are not the same. They are real numbers taken from the reals. In this case, we know the general solution. Remember how we had c1e to something? In this case, it's not e, it's x to the m1 plus c2x to the m2 for all x. That would be the general solution if m1 and m2 are not the same. Let's look at an example. If we're asked to solve x squared y double prime minus 2.5 xy prime, I put decimals in there, minus 2y equals to 0. Again, I'm not going to memorize the formula, but I'm going to derive stuff because it helps later on to help you to prove stuff and develop more tricks and strategies from this. So m x to the m minus 1, I need the second derivative, m times m minus 1 x to the m minus 2. Substitute x squared m minus 1 x to the m minus 2 minus 2.5x m x to the m minus 1 minus 2 x to the m equals 0. What do we get here? You multiply these together, m times m minus 1 x to the m minus 2.5 m x to the m minus 2x to the m. Divide everything by x to the m. Then m squared minus m minus 2.5m minus 2 equals 0. Combine like terms, and you can factor this out. You can multiply by 10 if you like, or by 2. 2m squared minus 7m to get your decimal points. And you get 2m m minus 4 plus 1. So m is negative 1/2 and m is 4. So the solution becomes, the general solution is c1 x to m1 plus c2 x to the 4th. Some people don't like to see negative exponents, so you can bring that down as the square root of x plus c2 x to the 4th. That's the general solution. So we solved it. First thing is, if you look at the equation that is given, so if you are looking at this on the exam and they ask you solve this equation, how do you know which method to use? Well, if you look back up, notice the equation has x squared coefficients. Do you see that? Like they have variable coefficients, like functions. That's why we thought about Cauchy Euler's equation. And the procedure is to take y equals x to the m and then find y prime, y double prime, depending. If it's a third degree, you find y double triple prime and substitute, simplify, solve as we did earlier. So that's the first case, when the roots are distinct. Case 2, when we have double or repeated roots. In this case, like m1 would equal to m2. And you know, this is when the discriminant is 0. So the roots in this case would be the roots of am squared, like the one we proved earlier, b minus am plus c equals 0 for this. And you can solve for m1. And from there, if you try to solve it, you need just to know the formula. It's c1 x to the m1. Because there's repeated roots, remember in the e before, when we had like c1 e to the x plus, or m1 plus c1 e to the m1, if this repeated, we threw an x there, and we proved where that came from. Here you can't throw an x there. What you throw here, guess what? It's natural log of x times x to the m1. Same, kind of like same idea, but there's natural log. And when did that come from? Again, if you run through the solution using quadratic formula and all that stuff, you will get this. So how do we apply it? Let's try to solve this differential equation. X squared y double prime minus 3xy prime plus 4y equals to 0 for him. So we have y equals x to the m. Y prime is m x to the m minus 1. Y double prime is m times m minus 1 x to the m minus 2. Substitute to get what? x squared, y double prime is m times m minus 1, x to the m minus 2, minus 3x, mx m minus 1, plus 4x to the m. Then m times m minus 1, x to the m, minus 3mx to the m, plus 4x to the m. You can divide everything by x to the m and get m squared minus m minus 3m plus 4 equals to 0. That gives m squared minus 4m plus 4 equals 0. Factor m minus 2, m minus 2 equals to 0. Then the solution to this, because it's repeated, general solution c1 x to the m1 plus c2 x to the m1 natural log of x. Substitute the m, c1 x squared plus c2 x squared natural log of x. Third case, case 3. That's related to complex conjugate roots. We have m1. If m1 is alpha plus I beta, then m2 would be complex conjugate. Alpha and beta are real numbers. In this case, the solution would be c1 x alpha plus I beta plus c2 x alpha minus I beta. But there's more different forms of this, different forms. On the right side, I'm going to write something here. If you have, what you can do first, rewrite this by breaking this up like so, I beta plus c2 x alpha times x to the negative I beta. So x to I beta, you can write it as e natural log of x I beta, because e natural log of x is x. And this becomes e I beta natural log of x. You can multiply the exponents. Why did I do that? Because now I can rewrite this as e I beta natural log of x. c2 x to the alpha e negative I beta natural log of x. So then for the first one, if you look back in the previous sections how we did it, you can, by Euler's identity, this by itself can be cosine beta natural log of x, like so, plus I sine beta natural log of x. Okay, plus c2 x to the alpha cosine beta x natural log of x minus I sine beta natural log of x. And after you can take this by itself and add them together and do the work, and then this will lead us to one solution, y equals x to the alpha c1 cosine beta natural log of x plus c2 sine beta natural log of x. So this is the case when we have complex conjugate roots. Complex conjugate roots. And we will see an example about how to apply this. So let's look at this one. If we are asked to solve x squared y double prime plus 7xy prime plus 13y equals to 0. If you try to solve all of this, you will get a characteristic equation m squared plus 7m plus 13 equals 0. m1 I got negative 3 plus 2i, but from the quadratic formula, and m2 is negative 3 minus 2i. So you can see that alpha is negative 3 and beta 2. So then the general solution would be x to the alpha c1 cosine beta is 2 natural log of x plus c2 sine 2 natural log of x. Okay, we can ask to solve x cubed y triple prime plus xy prime minus y equals to 0. Do you guys want to try it? Or we don't have time? So again, what we do, we start with y equal x to the m, get y prime, mx to the m minus 1, get y double prime, m times m minus 1, x to the m minus 2, get y triple prime, m times m minus 1, m minus 2, x to the m minus 3. So we found all of them, and we substitute. Let's see what we get. X cubed, m times m minus 1. You have to be patient while working with this stuff. Plus x, y prime is not this, it's this. Mx to the m minus 1 minus x to the m. So all these m's, you can multiply these, m squared minus m, and keep the m minus 2. When you multiply this and this, the 3's cancel, so you get x to the m. Mx to the m minus x to the m. You can factor x to the m out and get rid of it. So you get m cubed minus 2m squared minus m squared minus or plus 2m plus m minus 1 equals 0. So m cubed minus 3m squared plus 3m minus 1 equals 0. You got a algebraic equation we need to solve. How would we solve something like this? So to factor something like this, either by grouping, or you can use rational root theorem, or if you can find by inspection, that would be the easiest way. Like you can see, m equals 1 works. But what I'm going to do is I group the first one, the last one, and the middle ones. So m cubed minus 1, which is 1 cubed, minus 3m squared plus 3m. We have a formula for a cubed minus b cubed. It's a minus b squared plus m plus 1. Among these two, take a negative 3m out. That will leave m minus 1. So now you can factor this m minus 1 out. That will give m squared plus m plus 1 minus 3m equals 0. Group like terms or collect like terms. This is m minus 1, m minus 1. Oh, 3 repeated roots. So m is going to be 1, 1, or 1. And guess how the equation is going to look like? Y equals c1x plus c2x multiplied by natural log of x plus c3x multiplied by natural log of x squared. The next step I'm going to do, I don't want you to do all the work on all the stuff. We assume that we solved the equation and we got some of these answers. So we got m minus 1, m minus 2 squared equals to 0. How do you finish solving this? Then what? How do you get the final answer? You don't have to solve the actual equation, but the actual differential equation, I don't know what it is. I just randomly assume you got to the point like you did here, and then how you finish it up. So that's one thing. Another one, how about m squared plus 1 all squared equals 0? How do you finish also something like this? For the first one, we have m equals 1, m equals 2, and 2 again. So the general solution would be c1x plus c2x squared plus c3x squared natural log of x. For this one, it's m squared plus 1 being multiplied twice. If you want to solve it, negative 1, then m would be plus or minus I. Plus or minus I. The general solution would be c1 cosine natural log of x plus c2 sine natural log of x. That's from the first part. Plus c3, we have to multiply by natural log of x, cosine natural log of x, C4 natural log of x sine natural log of x. Anyone has any questions about this? How about if it's like this, x squared y double prime minus 3xy prime plus 3y equals 2x to the fourth e to the x. This is non-homo. So what do? We're going to be using variation of parameters from previous sections. Still we start, because it's Cauchy Euler equation, we still start with y equals x to the m. We get y prime m times x to the m minus 1, y double prime m times m minus 1 x to the m minus 2. That gives me x squared m times m minus 1 x to the m minus 2 minus 3x mx m minus 1 3x to the m 2x to the fourth. Well, we do it for the 0 for now, for homo. Simplify everything, you will get m squared minus 4m plus 3 equal to 0. Factor, so you get m equals 3 and 1. So yc is c1x plus c2x cubed. That's yc. We need to find y particular now, which, if you remember, is c1y1 plus c2y2. And from these two we get the general solution, which is yc plus yp. So we need to find what this is. The first thing we can do is divide the entire equation by x squared to get y double prime minus 3 over x y prime 3 over x squared y equals 2x squared e to the x. From this, actually from the previous one, from this one and this one, these are what we call them y1 and y2. And from this, that's f of x. What do we need these for? To find the Wronskian, which is y1, y2, their derivatives. So the discriminant is this times this, 3x to the third minus x to the third, 2x to the third. We do w1, where we replace the y1 and its derivative with 0 f of x and keep this the same. That gives us negative 2x to the fifth e to the x. And now we need to find w2. x1, 0, 2x squared e to the x. This gives 2x cubed e to the x. Remember, we need to find u1 and u2. So we start u1 prime is w1 over w. Simplify, you get negative x squared e to the x. From here, if you integrate both sides using integration by parts, that will give you negative x squared ex plus 2x ex minus 2ex. That's u1. u2 prime is w2 over w. So from here, u2 is e to the x. Then y particular is u1 y1 plus u2 y2. It's a lot of work, but fun. u1 is negative x squared e to the x, 2x e to the x minus 2e to the x times x plus y2 or u2 e to the x, and this is x cubed. If we simplify this, Negative x cubed e to the x cancels the last one. That will leave only 2x squared e to the x minus 2x e to the x. The general solution becomes yc plus yp c1x plus c2x cubed plus 2x squared e to the x minus 2x e to the x.